Great. Miki, you're welcome to start sharing your slides too if you're ready.
Sure.
And yeah, hi everyone. It's great to see you all here. Uh, are we are streaming. Perfect. Okay. So to welcome to our March Rocket Worlds discussions, Miki Nakajima from Rochester, who joins us today to continue our discussion series. So as a reminder of our etiquette, please use your full name on the Zoom. Hopefully keep muted through the talk and turn on your video if possible when asking questions at the end. So I will now turn it over to Miki to talk to us about magma ocean dynamics and Earth and super Earths.
Great. Let's see. Can you hear me? Okay.
Yes,
Yes.
perfect.
Okay, great. Yeah, thank you so much for the invitation. I hear all great story about this community. So thank you so much, and I love to yeah, I love to join the in-person meeting in the future if possible. So today, I'll be talking about a magma ocean dynamo in Earth and super Earth. So in today's talk, I primarily focus on two papers which published very recently. And let me switch to a laser pointer. Okay. Okay, so planetary magnetic field is very important because the planetary magnetic field can help preventing high energy particles reaching the planetary surface. So if you're interested in the habitability in within Earth or other planets, having a planetary magnetic field is already beneficial. And so far, the Earth is the only known terrestrial planet in the inner solar system that has currently have a strong magnetic field. And so here is the cross section of current Earth. So it has a rocky mantle and a liquid outer core and has a solid inner core. And the liquid outer core is convecting and it produces a magnetic field. And then there's a solid inner core. The solid inner core has a key role to produce the magnetic field. So the solid inner core cannot take as much light elements as the liquid outer core does. Therefore, when the solid inner core crystallizes, it releases the light elements to the liquid outer core, and also it releases a heat. So means that there is like a less dense material at the bottom of the liquid at the core that encourages a core convection and also dynamo generation. So this is the classical view of the dynamo generation in the current Earth. Um, However, this model likely may not have worked in the past. So the number of studies including the measurements of thermal conductivity of iron and also modeling studies indicate that the Earth's inner core may be fairly young, so perhaps younger than 1 billion years. And at the same time, the Earth likely had a dynamo by 3.5 or 4.2 billion years ago, based on the paleomagnetic measurements. So this suggests that the early Earth had a dynamo without the presence of the solid inner core. So this means that the early Earth dynamo mechanism may have been different from today's mechanism. And there are a few models that could potentially explain the early Earth dynamo generation. And the one idea is the exclusion model. So during the planet formation, like elements such as magnesium, silicon, oxygen, and many others were delivered to the core. And over time, the core cools, and then these elements uh, crystallize from the core as the MgO, SiO2, or others. So this means that the less dense material goes to the top and the more dense material goes to the bottom. Therefore, that would have created a core convection. And then that could have produced a dynamo without the presence of the inner core. And also, the study suggests that for early Earth, tides from the Earth could have been very strong, so that could have produced the core convection and also that dynamo generation. And also, there is an idea that the core also convected by pure thermal convection as well. And another idea is the dynamo generation in a basal magma ocean. So this is the remnant of a magma ocean at the from the planetary accretion stage, and it would have been enriched in iron, and the iron-rich basal magma ocean could have produced a magnetic field. So which I'll describe more in the next few slides. Okay, so we think that the planets, rocky planets, are created by number of impacts, and this shows one of our simulations, originally conducted by Scott Hall, who was a former PhD student in my lab, and he graduated. And it was visualized by the Roshan Mehta. He is an undergraduate student in my lab. And here color shows entropy that tells you the extent of shock heating. So this is the so-called canonical moonform impact. The proto Earth was hit by a Mars-sized impactor, and that shock hits the other part of the Earth's mantle, and this also in fact create a disk around the planet, and we think that the moon accreted from the disk. And then Earth must have experienced such a large impact in the past, and likely multiple impacts. And here is a cross-section of the Earth. So we previously did a scaling law to describe the size and the volume of the magma ocean as a function of impact velocity, impact angle, and the total target, the total mass involved the impacts and such. So yeah, so the yellow region indicates the molten magma ocean, and then dark region indicates a solid mantle, and this part is a core. So we think that a number of impacts happen to growing planets, and they experience multiple magma ocean stages. And again, planets, including Earth, likely start from a very deep magma ocean, but as the mantle cools, the magma ocean crystallizes. So in this image, this part is a magma ocean, this is a solid mantle, and here is the magma part, and here the core. So the magma becomes enriched in iron because iron is incompatible, so they prefer to thinner melt. And since iron is dense, this magma becomes more dense over time, and then moves to the core mantle boundary, and forming a so-called basal magma ocean, or BMO. And then the mantle continues to cool, and the solid portion increases, but the magma ocean can survive for billions of years because there's solid mantle on top, and this has a strong blanketing effect, so it's hard to cool the basal magma ocean. So this was originally proposed for the Earth, and here's a recent work done by Bukhari et al. And so in this work, they studied with the complete magma ocean, and they tried different magma ocean, adiabat, and also the liquidus. But so the conclusion is that it doesn't really matter much. So the melt usually migrates to iron usually migrates to the melt, and then that becomes more dense over time, and then usually form a basal magma ocean. So here, this figure shows the melt fraction, and this shows the temperature, this shows the composition, and this shows the melt, yeah. And the color shows the melt fraction, temperature, FeO content, and time goes this way to the right. And as you can see at the end of the simulation, the melt always forms, and that's iron enriched, and it's much more dense than the ambient solid. So the iron rich basal magma ocean is a very natural result of a magma ocean crystallization. And so people have argued that this could have happened to Earth, but perhaps other planets as well. So some studies indicate that Venus likely has a magma ocean, and the moon may have had a magma ocean that could be responsible for the early moon's dynamo. And seismic observations from the inside suggest that there is a molten silicate liquid layer at the core mantle boundary. So this also indicates the presence of basal magma ocean in solar system planets. And then how this could produce a dynamo? So here is the conventional equation that has been used well in the community. So here is the magnetic Reynolds number, and then and then here is the velocity, convective velocity. L is a convective length scale. Sigma is the electric conductivity. And if this number is larger than 40, that means that the magnetic induction is stronger than diffusion. Therefore, strong dynamo can be self-sustained. And I should also mention there is also recent work by Schiffer et al. And suggesting that in a BMO condition, this could be this number could be even more. It might have to be even higher to achieve self-sustaining dynamo. But in this talk, we go with this conventional number, which is 40. And the previous work suggests that the dynamo generation in Earth's basal magma ocean requires a very high electric conductivity, so conductivity higher than 10 to the fourth Siemens per meter. And so this is really high compared to any previous measurements. So it's achievable. But at the same time, we argue that the BMO is enriched in iron. And iron-rich oxide or silicate may have higher electrical activities than IV-free counterpart by orders of magnitude. For example, MgFeO could be the basal magma ocean analog material, which could have a much higher electrical conductivity than MgO. So therefore, the BMO may be able to produce a magnetic field. And the reason for this is that the iron 3D state contribute to high electron density at the Fermi level. So this could explain why iron rich the oxide or silicate have much higher electrical conductivity. And so far we talked about solar system planets, but this can be applicable to extrasolar planets. So here y-axis shows the planetary radius, and the x-axis shows the planetary mass, and the color indicate the equivalent temperature, and the reddish color indicate that planets likely have magma oceans. And as you can see, there are many potentially magma ocean planets. Therefore, magma ocean planets may be common in extrasolar systems. And we cannot directly observe whether a planet has a basal magma ocean or not, but we expect that many of them potentially could have basal magma ocean because the forming a basal magma ocean is a natural process due to the magma ocean crystallization. So in super Earth, magma ocean and basal magma ocean driven dynamo could be very common. So which is exciting. And so detecting magnetic field of these planets will be super exciting. So far, there are some robust detection of auroral radiation belt in ultra-cool dwarfs. And there are, so and then detecting magnetic field of exoplanets is a very active area of research. There are theoretical, but there are ongoing research on the theoretical and observational detection of magnetic field of exoplanets. And the method includes the detecting a radio aurora and the radiation belt and the star planet interactions. And let's get back to the this equation. It's the electric conductivity. And in this talk, we focus on MgFeO as a basal magma ocean analog material. And as I mentioned before, dynamo generation in Earth BMO requires the electric conductivity higher than 10 to the 4 Siemens per meter. However, the electric conductivity of solid MgFeO are much lower than this critical value. So this is a figure from Ota et al. And x-axis shows the temperature, y-axis shows the electric conductivity. And so here is a theoretical prediction, but previous measurements of MgFeO solid have much lower conductivity. And therefore, it's very important to measure the conductivity of MgFeO melt or the effect of iron under high pressures relevant to Earth and super Earth conditions. So that's the goal of our study. And yes, the first we measured the reflectivity of MgFeO, which is a magma ocean analog material, to estimate the electric conductivity by shock experiments. So here is the image of Omega EP, the shock facility at the University of Rochester. And so, yeah, everything happens in nanoseconds time scale. So therefore, we can't really measure the current and everything in such a time scale. So we have to measure everything in situ. So instead of directly measuring the electric conductivity, we measure the reflectivity, so how reflective material is. And using a Joule model, we estimate the electrical conductivity. And here is the just an idea, schematic view. So when the metal is conductive, that means that the free electrons are good conductors, so they can carry electric current. And at the same time, the free electrons tend to also contribute to reflectivity. So the metals tend to be usually shiny and also electric conductive. So these two quantities are related with the abundance of free electrons. And yeah, I also mentioned that the electric conductivity and DC conductivity. So DC conductivity is the electric conductivity when frequency is equal to 0. So which is a good assumption for planetary models. And yes, so first we'll talk about the super Earth regime where the pressure range is about 450 to 1400 gigapascal, which corresponded to BMO pressure over 3 to 10 Earth mass planets. And so these are the compositions of MgFeO target, and this work has been already published. And we also briefly talk about our ongoing work on the Earth BMO regime. The pressure range is around 30 to 140 gigapascal. And yeah, and then Alex Jasko, who is a graduate student in my lab, is presenting at the Lunar and Planetary Science Conference in coming weeks. So if you are going there, please stop by at his poster. And yeah, so I'm guessing probably not everybody is familiar with the shock experiments. I thought it would be fun to share some timeline. So 1 year before the shot day, so you submit the proposal, and so I'm guessing I'm never PI for submitting a telescope type, but I'm guessing it's somewhat similar. But yeah, so you write the proposal, and then you hopefully you're gonna get your shot day. And then once it's approved, you start preparing for your shot day. And yeah, about 6 months prior to the shot day, so you make sure you order all the parts and you figure all these specific plans. And 2 to 4 months prior to the shot day, you make sure to prepare targets. So this is a list of MJFEO target created by Alex. And of course, it takes time, and sometimes target breaks and you have to redo it again. So it's a bit stressful process, but then you bring the target to the target lab at our laser facility, and they assemble the other pieces. And 2 weeks prior to the shot day, so we finalize the pulse shape, the laser shape, and we communicate with the engineering team. Yeah, so we have a very excellent engineering team, and so yeah, for 2 weeks to the shot day, we communicate, we make sure everybody's on the same page. Then on a shot day, so there is not much you can do, although you can make decisions, but all the preparation should happen prior to the shot day, and then we work with the engineering team. So they have two teams, like morning team and afternoon team. And typically we shoot 10 to 12 samples, so starting at 8:45 a.m. and ends at 9 p.m. or so. So it's a long day and exciting and scary at the same time. So it's always an exciting day with some surprises. And so here is we are showing the our target design, and we have a ablator, and here's a quote. This is called the pusher, and we have a MGFO target, and it quotes ambio, with quotes fitness, and we shoot a laser to the plastic material, and that becomes plasma, and that sends a shock wave to the rest of the target. And again, as I mentioned, the shock happens in tens of, or even, yeah, few nanosecond time scale. So again, you have to do everything in situ. So the we measure the shock velocity using the visor, the velocity interferometer, and in this specific shock experiment, the everything is pretty much transparent, other than this ablator. And then when the shock passes, the shock is becomes reflective. So we always look at the shock front, and we also look at the temperature from the shock front using the strict optical pyrometer SOP. So we are observing everything in a shock front. And yeah, so, and then here we are showing the example visor data. So this axis shows the position, and this axis shows the vacuum velocity in orange. So what you see is these fringe motions, and the x-axis is the time. And again, we are always kind of looking at this shock front, and then this is where the shock front goes to the quartz pusher, and it goes to the quartz pusher and MGFO interface, and here it goes to MGFO interface and also quartz ambio, and then the shock goes to the vacuum. So you see these motions. And then you can figure out, okay, so what's the velocity change at these interfaces? And then you can estimate the velocity of the shock. So this fringe motion tells you the shock velocity. And also you notice that there are differences in color contrast. This part is darker than this part. So that means that this material quartz is more reflective than the MG FEO. So that color contrast also tells us the reflectivity. And as I also mentioned, we also use the measure the brightness, and then from that we measure the temperature. So we also combine this with the 1D planetary evolution model. So this work was led by Victor Lerm, and yes, so this is solving the planetary interior structure and also solving energy budget, and as well as the buoyancy profile, entropy budget, the magnetic field using a scaling law. And so here is also a schematic view of the 1D model. So we have inner core at the core, basal motion, lower thermal boundary layer, the adiabatic part of the mantle, and upper thermal boundary layer. So this is a very comprehensive model. So we don't have time to go through all the details, but this work is already published for the in 2024. This paper focuses on the Earth regime. In 2026, this focus on the super Earth regime. So if you're interested in the details, please take a look, or if you have any questions, you're welcome to ask at the end of the talk. And okay, so let's get back to the shock experiment part. So here we are showing the shock velocity as a function of particle velocity, and we measure the shock velocity, and then we are able to estimate the particle velocity. And these colors represent the different composition, different shots and the different compositions of MGFEO. So yellowish colors represent the MGO, and the greenish color represents MG 0.98, FE 0.12, and then bluish color represents the FE MG 0.95 and FE 0.15. And we also plotted previous shock experiments, and yeah, so we are experiments consistent with the previous shock experiments, and here's a fitting curve. And from that, we can estimate the pressure density relationship. And then we also compare that with the density functional theory, molecular dynamics calculations, which is also part of our work. And so we yes, at the given pressure, there's a little bit the density offset, but overall, our result is consistent with the previous MGO shock experiments and also the theoretical calculations. And we also find that the MgFeO and MgO have very similar density pressure relationship. So the iron didn't affect the density change that much, which makes sense as we don't have too much iron in the system. And then over here we are showing the reflectivity as a function of shock velocity and also pressure. And on the right, we are showing the temperature as a function of shock velocity and also pressure as well. And okay, so let's look at the reflectivity first. So this tells you how reflective material is. And this is also largely consistent with our new density functional theory, molecular dynamic calculations, so which is great, and also consistent with some of the previous work on the MGO. And as you can see here, we didn't really see a lot of difference between the MGO and the MGFEO, which was surprising. And on the right, we are showing the temperature as a function of shock velocity. And again, so same holds for this relationship as well. The temperature between MGO and FEO, MGFEO are pretty much the same. And yeah, so we think that the most of our shots are in the liquid phase. And yes. Okay. So again, also we are very happy to see the very good match between our shock experiments temperature and also the theoretical calculations, because our temperature estimate is not super direct, so there are always some uncertainties, but we are happy that they seem to be consistent. And here we are showing our estimate of DC conductivity. Excuse me, DC conductivity, again, this electric conductivity, then the frequency is equal to 0. And again, we find that the MgFeO and MgO have very similar electrical conductivity or DC conductivity, which was very different from previous estimate. So let's see. So we also show previous DFT-MD calculations here. So this line, which overlapping, indicates the conductivity of MgO and Mg 0.95, Fe 0.050, based on the previous DFT calculation. And previous work suggests that you need at least 0.25 iron contribution to have a very high conductivity. But that was not quite what we found, so it was very interesting to us. So we didn't despite the previous estimate, we didn't see that the iron we didn't see that the iron contribute electric conductivity by orders of magnitude. And but we have a potential explanation for this. So under these very high pressures, the MGO itself becomes very metallic. So the band gap of MGO closes at the high pressures. Therefore, MGO itself is very metallic, and therefore the iron contribution becomes minor. And that's why we don't really see a strong iron contribution. And the previous work was more focusing on the Earth pressure regime. So that could be the explanation. And based on this, we are now interested in the building electroconductivity model as a function of pressure and temperature. So as you may have seen before, let me bring the previous slides. So you can see the temperature is actually so much higher than the regular planetary temperatures. Then we had to correct this temperature effect. And yeah, so so that's what we are doing here. So we made a model, conductivity model, as a function of the pressure and temperature so that we can apply a model to planetary regimes. And so here we are showing the electric conductivity of basal magma ocean as a function of planetary mass normalized by the Earth mass. And So here, the different colors represent different core mass fraction, CMF. So ours is here, it's close to Earth's core mass fraction. And this means that the core is relatively small, about 28%. And here, this is a more like a bigger core environment. So it's close to Mercury environment. And so here shows the estimate of the electric conductivity at the the basal magma ocean in these super Earth planets. So this is based on our experiments. And the line here shows the model. So that is the required minimum electric conductivity in the basal magma ocean to produce a dynamo. So this means that if this dashed line is higher than this model value, then it means that the BMO-driven dynamo can be produced in the super Earth environment. So based on this figure, we argue that planets larger than 3 to 6 Earth masses can have a BMO-driven dynamo. And here we are showing example calculation. So y-axis shows the magnetic field strength at the surface, and the x-axis shows the time. And we have different models, but for now, let's focus on the base fit model. The gray shows the core-driven dynamo, and the orange shows the BMO-driven dynamo. And here we are focusing on the 6 Earth mass planet. And you can see that the BMO-driven dynamo could be much stronger than the core-driven dynamo for billions of years. So we are arguing that the BMO-driven dynamo could be the primary dynamo source for super Earth for billions of years. And yeah, so now we show the one case scenario, but here we are showing this comprehensive results. Here, the y-axis shows the planetary mass normalized by the Earth's mass, and the x-axis shows the time. And in this specific figure, we fix the core mass fraction to 0.32, and the color represents the BMO magnetic field strength normalized by the core magnetic field strength at the surface. So if number is larger than 1, it means that the BMO-driven core is stronger. And you can see the magnetic field strength depends on the size of the planet. But generally, you can see that the BMO-driven dynamo is stronger when the planetary mass is large enough. So this is partly because larger planets have a larger pressures, therefore the electric conductivity is high enough to produce a dynamo, and also the planetary mantle becomes large, therefore the convective regime of the BMO typically increases, therefore that tend to make the BMO-driven dynamo efficient. But there are also like a BMO-driven, BMO-only situation, like core dynamo situations. But typically there are most likely these planets have a BMO-driven dynamo and a core-driven dynamo as well. And on the figure on the right, we are showing the core mass fraction as a function of time. And here we are fixing the planetary mass. And as you can see, relatively smaller the core mass tend to produce a strong BMO dynamo. But if the core mass is so strong, then there's not much BMO, therefore it's hard to produce a dynamo. So it becomes a core-driven dynamo. So key message here is that typically the BMO-driven dynamo tend to be stronger, but it also depends on the planetary mass and also core mass fraction. And here's another figure. So the y-axis shows the planetary mass normalized by the Earth mass, and the x-axis shows the core mass fraction. And so the color indicates the minimum electric conductivity required for BMO-driven dynamos. And the green shaded region shows the sort of forbidden region where the BMO-driven dynamo is impossible based on the previous work by Six Root et al. And the sky blue shaded region shows the same, but based on our latest work. So this suggests that the BMO-driven dynamo depends on the conductivity model and also core mass fraction, but typically relatively small core mass fraction with a large planetary mass planets tend to produce a BMO-driven dynamo, and they tend to be stronger than core-driven dynamo. So this is a topic about the super Earth, and let's briefly talk about the basal magma ocean within the Earth, and this is certainly still ongoing work, but I'm here sharing the exciting work done by Alex. So here y-axis shows the reflectivity and x-axis shows the pressure. So this is coming from his LPSC abstract, and again different colors represent different MJ field compositions. Here we are looking at more iron-rich scenarios, and these experiments are actually much harder than the more iron-poor scenarios. And so far, we are still analyzing a data set, but still typically we see that iron content doesn't really affect reflectivity. And so this suggests that iron doesn't seem to contribute to a high conductivity based on our estimate. So which is pretty interesting, and it still doesn't it's not fully consistent with the previous theoretical estimate. So we are still trying to figure out what's going on here. And also here is our theoretical work, which was published in 2024 for Earth's BMO regime. And again, the electrical conductivity at the Earth's BMO pressure regime is not constrained by our experiments, but for now we assume this value for this modeling part. And here is the magnetic Reynolds number. We use critical value of 40, and this number, the magnetic Reynolds number is higher than the specific value, then dynamo generation is possible, and with the BMO and core as well. And again, let's focus on the best case scenario. And on the right, we are showing the magnetic field strength at the surface as a function of time. And then we predict that the Earth's dynamo could be produced in a BMO first, followed by a core-driven dynamo. And our general magnetic field strength seems to be consistent with the paleomagnetic record. But again, we are still working on constraining the magnetic field, the electrical conductivity at the Earth's pressure regime. And also in the next few slides, I just want to highlight some of the contribution from my group. So especially here going to the lunar and planetary science conferences. So here again, we mentioned Roshan's work, but he's presenting at the LPSC. He's giving a talk. And so we talked about our previous scale, so we estimate the magma ocean volume as a function of impact velocity, impact angle, and also total planetary mass and such. But at that time, we didn't really look into relatively small impactors because of the resolution issue. But now Roshan is running a very high resolution simulations where we can see a very small impactor. So gamma is an impactor to total mass ratio. These are very small impactors. It has important implications for planetary evolution. And we are finding that our scale is okay for relatively large impactors, but small impactors, our previous scale massively underestimates planetary melting. So yeah, so we are he's presenting at LPSC, and we are preparing to finish up this work. And if you are going to LPSC, please go to his talk. And I also want to highlight another presentation done by Kim Kong. She was a former postdoc scholar in our group, and so she conducted shock experiments on the lunar rock analog material, and she observed the phase transition of zircons to rhyolite, as rhyolite is a higher pressure version of a zircon at the when the pressure is higher than 20 gigapascal in the shock experiments, but not always. So this indicates the absence of shock features on the lunar samples do not necessarily mean no shock. And it has an interesting implication for impact history on the Earth and the Moon and elsewhere. And moving on to the conclusion. So to conclude, we model, our experiments are consistent with the density functional theory, molecular calculations, and previous work. And despite previous predictions, MgFeO and MgO have very similar electrical conductivities at the high pressures. And the reason is that at high pressures, the MgO becomes metallic, therefore iron has minor contribution to the electrical conductivity. And then we also predict that planets larger than 3 to 6 Earth masses can have BMO-driven dynamos, which tend to be stronger than core-driven dynamo for the first few billion years. And again, we are still working on estimating the electrical conductivity within the Earth pressure range. So please stay tuned. But based on the model, the Earth may have had a BMO dynamo for the first 1 billion years, and then followed by a core-driven dynamo for the rest of the history. And again, if you are going to the APSC, please say hi to our awesome team members. So thank you very much for your attention.
Good. Thank you so much, Miki. I thought that was a really exciting result. Do you have any questions? Don't be shy. Hey, maybe I'll ask a question then. So I've been wondering how the volatile content of the magma ocean affects whether or not you can sustain a BMO, just because if you have more volatiles, you'll make the everything less dense. Not sure if you know that.
Sure. Yeah, that's a good question. Yeah, please correct me if I'm wrong, but I'm guessing. Yeah, guessing. So it could be completely wrong. But I
Yeah.
think volatile, yeah, depends on pressure, but volatiles tend to, yes, less dense and want to escape from the magma ocean. So I would imagine that if you are starting a full magma ocean, the also again depends on how fast the mantle magma ocean is convecting, but yeah, I think the volatiles tend to want to escape, and then BMO wants to go to the bottom. So there could be some trapped volatiles, but I guess probably not strong, like not enough to make it less dense. That's my guess. Because iron doesn't make it really dense.
Cool. Thanks. Hey, do I see any questions?
I think I see Stefan.
Yes,
Oh,
yes.
sorry. Okay, go ahead. Thanks.
Hi. Thanks a lot for the presentation. It's great to see all this work. I was curious about the MgO becoming metallic. I didn't catch. I mean, is it liquid in the experiment or is it solid? I mean,
Yeah, it's
does it
liquid.
make a difference?
Yes, so let's see. Yeah, so typically yeah, let's see. Let me go back to the phase. So it's possible that some of our measurements we suspect like okay, there's some part that becomes this part. There was a long discussion about this part. I go, is it like solid or is it something else? So we got confused. So it's not impossible that the some part of the experiment might have been solid, but most likely most of them are
Okay.
liquid. And we expect that the liquid has a higher electrical conductivity. But it kind of also depends on the pressure range and such. But yeah, so in our experiments, we didn't see a record like a clear record of solid liquid or clear record of post-impact shock. So we saw a liquid. But in the more new experiments where Alex is doing, we think that this is solid.
Okay.
And if you have any insights, let us know. But I think you looked on the literature and the solid and liquid MG, the conductivity seem to be not that different in the pressure range. But we kind of had to make a model switching from solid to melt when we are doing modeling. But yeah, in the low pressure, it's kind of hard to make it melt because the
Yeah.
ammonia is hard. Yeah.
And in terms of thermal conductivity, I mean, if it's metallic, you would expect the Wiedemann-Franz law to apply, or what's the?
Yeah. Yeah, I think it's a metal. We would think. We would think. Victor actually did look into this, like, if you wanna have a electrical conductive, like high conductivity material, it could also have a high thermal conductivity, and then that might make it difficult to produce a dynamo. So there is some counter effect. But
Yeah.
yeah, we are still able to find a regime where the electrical conductivity is high enough to produce dynamo, but the thermal conductivity is low enough to have it convect.
Okay. Okay.
Yeah, but unfortunately, we cannot measure the thermal conductivity. It would be super cool,
Yeah.
but it's very difficult. I feel
Of
like I'm
course.
still new. I'm still,
Yeah.
learning things. And yes,
Yeah.
it will be super cool.
Of course. Yeah, I mean, otherwise, I guess, I mean, okay, you mentioned the Schaeffer paper, and
Yeah,
of course, I mean, it seems to be very critical, the value of the threshold for dynamo action, and actually there's the threshold for dynamo action, and there's what is needed for strong
right.
field dynamo action, and it's of course higher. And
Yeah,
it seems to me
yeah,
that I mean the conclusions for super Earth. I mean it's very clear that it could drive a dynamo.
right.
I guess it's more marginal for the Earth's case. I mean it's more uh, difficult, I guess.
Yeah, that's what I'm feeling. So, so this is the figure from Victor's recent work. And so, well, thank you for sending a paper when we got it. We already in a accept phase, so we couldn't make too many changes. But yes, so I think that also probably could affect all the shaded regions. And I do still think that for big super Earth planets, the BMO-driven dynamo is likely, but again, specific critical mass and such could depend on the model. But for Earth, based on the previous work and ongoing work, I feel like it's challenging. It is.
Yeah. Yeah.
But stay tuned, please.
Yes, yes.
Yeah.
Thanks a lot.
Yeah, thank you.
Thanks. Any more questions? I don't see anything, but also I might be missing something because, okay. Oh, yeah, Hannah, go ahead.
Hi, thanks for a great talk. I am very new to how these experiments work, so I was just wondering if you could give us insight into what is the biggest source of uncertainty in your conductivity measurements when you have to get them from these experiments.
Many. Yes. But let's see, biggest source. Yeah, there are many challenges, I guess. Let's see, I don't know where to begin, but okay, so let's see. Yeah, okay, sometimes for like high pressure experiments, like high, like 1 terapascal kind of pressure range, it becomes less important. But for example, you see this kind of thing, right? So this is coming from glue. So glue is always like making everything a little bit difficult. And also like index of refraction is also really important. And we assume that MGFEO has the same index of refraction with MGO, which is probably okay for the targets with low iron content, but probably it's not okay for more iron-rich scenarios. And it's also hard to measure that for opaque materials, like the index of refraction for opaque materials. So we are scratching our head. So glue, glue, and the index of refraction are enemies, kind of.
Great, thank you for explaining.
Yeah.
Thanks. Any last questions for Miki before we wrap it up? Okay. If not, last chance. Okay. If there's no more questions, then let's all thank Miki again. This is a really fantastic discussions. And hopefully we will see most of you again next month in April for a talk by Anna Place. Thank you again and goodbye.
Yeah, thank you so much. Have a nice
Thanks.
rest of the day.
Thank you.